Solving calc problems is a lot of fun. Let's find these solutions. Let's get it done. I just adore the tools we use. Ba-dum, ba-dum, bum, ba-dum, ba-dum, bum, bum, bum. All right, quiz 11. Ooh, the end is coming near. Okay, let's have some fun. So, number 1. Convert the integral, it's triple integral, 0 to pi, 0 to 1, 0 to root 3r, r squared sine theta, dz dr d theta, from cylindrical coordinates to Cartesian coordinates with order dz dy dx. Now, of course, it tells us that it's in cylindrical coordinates. I mean, it just comes out outright and tells us. I mean, that's no fun. But we actually don't need that hint. You see, that's given to us. And how do we see that it's given to us? Well, the fact that we see z, r, and theta. Those are the types of symbols that we use when we're talking about cylindrical coordinates. So let's sort of tear this apart a little bit and see if we can't get a better understanding. So I'm going to rewrite it for just a moment here. 0 to pi, 0 to 1, 0 to root 3 times r. The root 3 does not, the square root is only attached to the 3, not to the r. It's hard to tell, but if you look, it really does stop at the 3. Now, let's think about this last part, dz dr d theta. What we really want to do is at the end, that should be our dv. In cylindrical coordinates, dv is r dz dr d theta. This r is important. So we're going to take one of the r's here and pull it off to the end. So I'm going to have an r sine theta, and then r dz dr d theta. So this part right here, that's our dv. Okay, that's not so bad. That means that this part right here, this is our function that we're working with. So we're just going to have to work with that in just a second. And now, of course, we have our bounds. So let's think about what our bounds tell us. So going from the outside, theta is going to go between 0 and pi. R is going to go between 0 and 1. Now, if we stop with just that piece of information there, 0 to pi, 0 to 1, that's actually enough to tell us a little bit about what's happening in the plane. So 0 to pi is in the top half, 0 to 1 says we're going out to the unit circle. So that's our region here in the xy plane. All right. So that's what this corresponds to. Then we go from 0 is less than or equal to z, less than or equal to root 3 times r. Now, we have to make sure we understand this. So, first off, the bottom is pretty easy. Z equals 0. That's simply the xy plane. No big surprise there. Now, z equals root 3 r. That's not so clear, at least not until you get the hang of these things, and we may not be there yet. So one of the ways you can think about it is just start by working what I like to call the RZ plane. It's really kind of a half plane. And you said, well, if z equals root 3r, you'd have something going up at a pretty steep angle. It's not 45 degrees, it's a little bit steeper than that. Z equals r would be 45 degrees. All right, so now what happens is if you spin that, then the shape that you spin this out to be is the surface that you produce. So in this case, what the surface we're producing here is a nice little cone. Okay? So z equals some multiple of r is a cone. That may or may not come into play, but all right. So suppose we were to put all this information together. Well, what would we have? If we were in the x, y, z space, you see here that we want this circle. So I want to take this circle and put it in. And if we do that, so watch carefully. So this circle here, it would come in to there. Okay, so that's half circle goes in there in the xy plane. And now what's going to happen is we're going to go from the xy plane, that's z equals 0, up to this cone. So now I have this cone that's coming out, and I'm going to go up to the cone, and let's see, it looks something kind of that-ish, and something like that. And you might be saying, I'm not quite sure I see what that shape is. So what this is, and I haven't done the best job of it, but in some sense you can think of it as sort of a cylinder. Let's start with that. Then we drill out a cone. All right, that's not so surprising. And then we cut it in half. And that's sort of a description of what our shape looks like. And so, okay. So how do we go and convert it into Cartesian? Well, it's not so bad. In fact, probably, if anything, we've done too much. So integral, integral, integral. The function. So I need to convert r sine theta in terms of x, y, and z. Well, that's not bad, because r sine theta, that has a corresponding term in polar. R sine theta is y. Now what about the dv? Well, that's the dz, dy, dx. So this last part here is dz, dy, dx. Now I think about the picture. So let's start with the xy. So that's this picture. And we can see, for x, we go from -1 to +1. So -1 to +1. Now, you can imagine that, all right, I have some x. Where does the y go from? In other words, as I'm moving up and down here, well, I'm going to go from this bottom, and that's y equals 0, all right, up to the top half of that circle. Now that circle is, all right, as x squared plus y squared equals 1. Solving for y, because I want, this is a y bound, so it's a y equals y squared equals 1 minus x squared. And I take the positive square root, because it's the top half. That's why it's the positive square root. So I go 0 up to square root 1 minus x squared. Now, how about for z? Well, for z, that's not so bad. We come to the three-dimensional picture. We say, look, we start at z equals 0, and then we go up until we hit our cone, z equals √3r. Well, I need to convert this. So let's convert that. I haven't converted that into our Cartesian. So r is the square root of x squared plus y squared. That's just one of our nice facts. R squared equals x squared plus y squared. So we're going from z equals 0 up to the square root. And I can just combine these two square roots together. 3 times x squared plus y squared. Now, the next thing to do is to circle the answer, because we're done. That's it. We did the conversion. So life is good. Woohoo! Nice. Nice. Because this is just about converting. We don't actually have to find the value of the integral. We could. We probably wouldn't have a lot of fun doing it, but we could. But for now, we won't. We'll just stop here. Now, we're not going to take that away, because on our next problem, you might notice something. It says, convert the integral, exact same integral from cylindrical to spherical. So we're going to go through and just sort of say, let's not reinvent the wheel. So we have a couple of things going on here. So I'm just going to copy bits and pieces that we have from here. So, for instance, we can say we have what? Well, integral 0 to pi, integral 0 to 1, integral 0 to √3 times r. Then we have our r sine theta and our r dz dr d theta. Same as before. This last part is dv. This is our function. And if we're looking at our picture, and I'll sort of try to re-sketch our picture, maybe I'll be even better this time. It's possible. Weirder things have happened. We know that in terms of the xy plane, we're this half circle, and then we're going up to a very particular cone. And so that's our basic shape. And it's our solid inside of here. Okay, so I'm not going to try to rederive too much. I will say it's useful when you're working in things to look in sort of a slice. So I like to think of this as R and Z. And so here we have this Z equals root 3R. And we're going to use that to figure some things out. All right. So our goal now is to get a handle on what will this become in spherical coordinates. So let's write down the start. Integral, integral, integral. Our function. Now, in spherical coordinates, so spherical coordinates, you might remember, that means we need things in terms of theta, phi, and rho. So, theta, phi, and rho, the sine theta, that's perfectly fine. We keep it as is. Now the r, that does have to change. So what we get is we have some basic facts. For instance, z equals, we could call it rho cosine phi, and r equals rho sine phi. So I can replace the r by rho sine phi. The sine theta I'll leave as is. So that's rewriting our function in terms of our new variables, theta, phi, and rho. The dv, well, we just have to remember the song. Rho, so that's rho squared, sine of phi, that's sine of phi, d rho, d phi, d theta. Okay, there you go. That's our dv. Now, how about our bounce? Well, theta acts the exact same. So in other words, whatever it did in cylindrical, it's going to do in spherical. So if theta was going from 0 to pi before, it's still going from 0 to pi. That's really no surprise. Now how about phi? Well, if you think about the picture here, and I'm going to actually be a little bit more precise here. So I'm going to go out here to r equals 1. And what's happening in this picture is I'm taking this slice here, a little triangle, and this is what I'm going to spin halfway around. That's what forms my shape as I form it here. Now, if I'm after phi, the real question becomes, what's the angle off of the positive z-axis? So I need to know what's this angle until I hit the line, and then what's this angle until I stop. Well, this angle is actually pretty simple. So that corresponds to when do you hit the xy plane, and that's a fairly well-studied angle. That's the angle pi over 2. Now this other angle though, that's more interesting. All right, well let's take a closer look at this triangle that we've drawn. Now it's not just any kind of triangle, in fact it's the right kind of triangle, where the bottom side has length 1, this right-hand side has length root 3. Now if you use Pythagorean theorem, 1 squared, square root of 3 squared is 3. That means the hypotenuse squared would be 4, meaning this has length 2. This is actually a very famous triangle. So why is that helpful? Well, it says that this corner down here, if we were in, say, a trig class in high school, we'd say, ooh, that's 60 degrees, and that corner up there is 30. Of course, that's if we were in trig. We're in calculus. So we say, ooh, this angle, that's like pi thirds. and that angle, that's like pi 6. But wait, I don't need this angle in the corner. I need this angle coming off the positive z-axis. Well, it turns out, this is kind of convenient, that the angle coming off the positive z-axis, so this angle that I'm after, is going to match with that angle there. So in other words, that's an angle of 30 degrees, or I start at pi 6. Now, the last thing is rho. Now, how do we think of rho? Well, for rho, we always think about we're coming out from the origin. So that's how we start. So here's the origin. So I'm going to just start coming out until I hit my curve. All right. Now the question is, well, where do I start? Well, I start at 0. All right, well, that's fair, perfectly fair. Where do I stop? I stop when I hit, in this picture, it's the shell of the cylinder. So I'm going from the origin out to this cylinder, r equals 1. Now, the problem is r equals 1, that's the wrong coordinate system. So we've got to change that. Well, we know what r is. That's rho sine phi equals 1. Now, when I'm talking about my bounds, because see, this is a d rho, that means I need a rho equals. So I need to get rho by itself. Oh, that's not so bad. Divide both sides by sine. Rho equals 1 over sine, which is also known as cosecant. So that cosecant is really corresponding to what we would call the edge of the cylinder. All right. Now we can clean this up a little bit because we can combine certain terms on the inside. And so if we do that, combining things together, we get that this is 0 to pi, pi over 6 to pi over 2, 0 to cosecant phi. Then we have rho squared, so that's rho cubed. Sine times sine is sine squared phi, and then there's a single sine. And d rho, d phi, d theta. And that is the conversion into spherical coordinates. And there you go. Life is good. Life is great. All right, that's number 2. Cool. It's nice. We got to do a little bit of recycling of our work. All right, number 3. Set up, but do not evaluate. Some of our favorite words. An integral in spherical coordinates. Okay, so we're going to work in spherical. Nice. To calculate the volume of the region inside the surface is x squared plus y squared plus z squared equals 9. Below the surface, z equals root x squared plus y squared. And above the plane, z equals 0. So let's talk about this. We want to be inside this surface. Now this surface is actually a really easy surface. X squared plus y squared plus z squared equals 9. That's going to be a sphere of radius 3. So we just draw a sphere. So it's actually, we can even say more, it's a sphere of radius 3 centered at the origin. So that says be on the inside. All right, so we're inside our sphere. All right, cool. That's number 1. Now, number 2, we have to be below the surface. Z equals root x squared plus y squared. Now, that surface is actually one we see a lot. That's the cone. So there's our cone coming up, and we want to be below it. So that says we're down here, down below. Okay? So we're below the cone. And the last thing we want to do is we want to be above the plane z equals 0. Now z equals 0, what's that? Well, that is the xy plane. This is z equals 0. And so we want to be above it. So that says, we're up here. Right? We're above z equals 0. Now, when you put all these together, you have to sort of think about what it might look like. So for example, if you combine the first and the third, we see, it's the top half of the sphere. And then this says below it is we're sort of I like to think about drilling out ourselves a cone. So what does this look like? Well, something vaguely like the following. And we're just going to do a really rough sketch right now. There's a sphere. We have this cone coming out, and then it looks okay. All right, you have to pretend like I'm a good artist. So that's essentially what our shape becomes. So it's again, it's a sphere with the top half of a sphere. It's the hemisphere, but the cone's been drilled out. All right, yeah, that's kind of right. Okay, good. That's at least enough for us to get going. Okay, so now we have to start thinking, okay, what do we need? Well, we need to find volume. Well, how do you find volume? Well, volume is actually really easy. See, if I'm looking for a volume of a region, what I can do is I can just integrate over my region. So it's a triple integral. By the way, how do I know it's a triple integral? Well, because I'm working in spherical coordinates. So that's really a triple integral, three-dimensional integral, over my solid of 1 dV. Okay, so that's what I need to do, where here's my solid S. So, well, so this will become integral, integral, integral. Now 1, super easy to do 1. If I want to convert 1 into spherical coordinates, 1 becomes 1. All right, how about dV? Ah, yeah, remember the song, rho, rho. See, that's rho squared. Sine of phi, d rho, d phi, d theta. Merrily, 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 calculus is a dream. Oh, great song. All right, now let's stare and see if we can't figure out some bounce. First off, our theta bounce. Well, look at the picture. See, this is going all the way around. That means that theta goes 0 to 2 pi. All right, that's easy to see. If you have complete symmetry around the z-axis, which is what we have here, then theta goes 0 to 2 pi. No surprises. How about phi? Now, what I'd recommend for that is let's look in our slice. So when I'm thinking of slice, I'm thinking of r and z. So what I have is that this surface, z equals root x squared plus y squared, it becomes z equals r. And then this surface, x squared plus y squared equals 9, it's like we took a circle of radius 3 and we just drew it in. So there's our circle of radius 3. And the reason I have that dotted line is what our shape comes from is we're spinning around, and the part that we're spinning is this part over here. All right, so that's what we're going to do to find our area. Excuse me, find our volume. All right, so we're almost there. We're almost there. Okay, so we just got to bring it home now. Let's think about phi. So phi, that's going to ask what are the angles as we come off of the positive z-axis. Well, the angle from the positive z-axis to z equals r, that's coming out at 45 degrees, so that's pi over 4. Then to go to the xy plane down here, that's pi over 2. All right, well that's not so bad. And finally, our last piece is how do we get our rho? Well, rho says start from the origin and go out. So what do we start at? Well, we start at rho equals 0. And where do we stop? Well, we stop when we hit the sphere. So the thing stopping us is the sphere. That's the outer surface. So x squared plus y squared plus z squared equals 9. That's the sphere rho squared equals 9, or rho equals 3. So we're going 0 to 3. Now, the next thing for us to do, it's also the last thing for us to do, is to say, we're done. We've now set it up. And that, lo and behold, will give us the volume of this kind of curious and fun looking shape. All right, cool. These are actually fun. In some sense, what's being tested here, we're not really testing the calculus part because there's no calculations being done right now. Eventually we'll get to some parts where there's calculations being done. But what's being tested is geometry. Do we understand what shapes look like? Do we understand how to describe shapes? And once we understand that, well, then the rest of it, it's just fun. And if we don't know how to do it, well, forget it. It's hopeless. Go back and practice some more. Because, well, the more you practice, the better you get. Number 4. Evaluate the following integral. Integral 0 to 1, integral root 1 minus y, integral 1 minus y to 4 minus y, y e to the root, that's where the root is coming from, x plus y, dx dy, by making change of variables. U equals square root x plus y, and v equals y. And there's some cryptic note here. Note, integral of u e to the u is u minus 1 e to the u. I don't know why we'd need such a cryptic note, but hey, who knows? Who knows? Let's play around with this. Let's see what we get. Now, so how do we approach this? Well, whenever you're changing variables, you always need to sort of do 3 things. And so here's sort of my thought process. We want to sort of how we split things up. And this is the Jacobian. So I like to do that first. Then there's the function. All right, what does our new function become? And that says I want it to go to terms of u and v. And then the last part is our bounce. So let's start with how we split things up. So what we're going to do is we're going to do the following. So I'm going to think of this I'm going to write this as really x plus y to the 1/2 power. And here's what I like to do. I'm going to look at u sub x and v sub x and u sub y and v sub y. I oftentimes get these all jumbled up. But the nice thing is the Jacobian is very forgiving. And as long as you'll see, like, for example, the u and the v were the columns, the x and the y are the rows. If you have some sort of system that more or less does that, life is good. So this is going to be a function of x and y. So let's figure out what these partial derivatives are. U sub x would be 1/2 x plus y to the minus 1/2. And then v sub x will be 0. U sub y, 1/2 x plus y to the minus 1/2. And v sub y will be 1. Okay, well that's not so bad. So what does that say? Well, that says this is, take the 2 by 2 determinant, you'll get 1/2 x plus y to the minus 1/2. Now, how does that information help us? Well, what it says is it says the following. du dv is equal to the absolute value of this. Well, it's not going to be negative, so 1/2 x plus y to negative 1/2 dx dy. So, if I had 1/2 x plus y to minus 1/2 up here, that would tell me, hey, I should pull it aside and use that to become part of du dv. I don't actually have that right now. That's okay. Because I can now rewrite this and say, another way to think about this is that dx dy, cross multiplying, is 2 times this. See, this is in negative 1/2, so when it comes across, it'll be a positive 1/2. So I can think of the square root of x plus y, and then I have du dv. Well, square root of x plus y is u. So that's 2u du dv. All right, so that's splitting it up. Okay, good, good. Well, what's the next part? Well, the next part usually is pretty quick. See, we still have the whole function. We haven't used any part of it yet. See, sometimes you use part of the function when you're making your substitution, sometimes you don't. Here we didn't. So we say, okay, well, how can I write y in terms of u and v? Well, that's easy. That's the v. How can I write square root of x plus y in terms of u and v? Oh, well, that's the u. So it's v e to the u. Okay, we've got our function in terms of u and v. See, like I said, that one's usually the fun part. Now the interesting part. Okay, so let's think about our bounds. Okay, so let's figure out what the current bounds are. So on the outside, we're told we go from y equals 0 to y equals 1. Yes, see, y equals 0 to y equals 1. And then we go from x equals 1 minus y to x equals 4 minus y. Now, if we sort of do a quick sketch, and we are going to actually do this, this curve, this is the curve x equals 1 minus y, is really the same as y equals 1 minus x. So you come over here to 1, and you have a slope of minus 1. So it looks something like that. So there's a 1. All right, and then this 4 minus y, well, it's like you came up here to 4, and again, you have a slope. Why? Because it's the same process, y equals 4 minus x. Now, those are our curves, x is a function of y, and then we're also told y equals 0, which is here, to y equals 1, which is there. So we have our region is that region. So there are 4 bounding curves. And what we want to do is we want to say, let's look at each curve and think about how to write them. So some of them are pretty simple. We get y equals 0, y equals 1. Then here, I'm going to write it as not x equals 1 minus y or y equals 1 minus x. I'll just write that as x plus y equals 1. And the other one is x plus y equals 4. Now that's how to write them in terms of x and y. We want to get our bounds here. We again want to get these in terms of u and v. So what does y equals 0 become? Well, y equals v. So that becomes v equals 0. Y equals 1, v equals 1. X plus y equals 1. Well, x plus y shows up here in terms of u. So if x plus y equals 1, that becomes u equals the square root of 1, which is 1. X plus y equals 4, well, that's the square root of 4, which is u equals 2. So this here is the x, y plane. In terms of the uv plane, we're going to go from u equals 1 to 2, and, whoop, can barely see it there, 1 and 2, and v equals 0 to 1. So it's a nice little rectangle, easy to describe. All right, so now let's put all of this information together and see what we get. So here we go. We have integral, I'll start with the current integral, 0 to 1, 1 minus y to 4 minus y, y e to the root x plus y, dx, dy. Now, before we get too far along, we do have to make a decision, which is this dx, dy, I can write it as 2u du dv or as 2u dv du. I do actually get the freedom to make a choice, which is the choice I get to make is how should I integrate? Well, let's start with just du dv. If we get stuck, we'll go back and try it the other way. So the dx dy becomes 2u du dv. The y, e to the root x plus y, well, that becomes v e to the u. Okay, so have you seen where our pieces come in? dx dy, and then the v e to the u. Yep, okay. Now the bounds, we got to go to the picture. Well, we can see, look, our V bounds, the outer layer, does what? Well, we go from V equals 0 to V equals 1. The inner layer does what? That's 1 to 2. Okay, so we got to carry out this integral. Now, in fact, we can do one of our old favorite tricks. You see, this can really be written as the integral 0 to 1 of 2v dv times the integral 1 to 2 of u e to the u du. Now, why can we do that? Well, our bounds are a nice rectangle inside of the uv plane, and our function we can write as a function of v times a function of u. And now we just have to do each piece. Well, the integral of 2v is v squared. Evaluate that from 0 to 1. Now we got to integrate u e to the u. How could we do that? I wonder how we could possibly find a way to integrate u e to the u. Oh, wait a second. They gave us a hint. Oh, they are nice people. They care about us. So this is u minus 1 e to the u. And we're going to evaluate 1 to 2. Well, on the first one, v squared from 1 to 0 will be 1 minus 0. So that's just 1 times, when we plug in 2, 2 minus 1 will be, well, it's 1 times e squared. Subtract 1 minus 1 e to the 1. Well, that's just 0. And 2 minus 1 is 1. So we get 1 times e squared, giving us our final answer of e squared. And that's it. We're done. Good. I see that we sort of went the opposite. Normally we go left to right, but today was right to left. But that's okay. It's not that any one single piece is hard. What you have to pay attention to is, all right, what's the process? Okay, figure out your Jacobian, how you split things up, do work your functions, get the bounding curves, rewrite the integral, off you go. Life is good. All right, well, let's try some more. In fact, I think we're going to have a couple of these, so this will be good practice for us. Number 5, compute the integral 0 to 1, integral from minus y cubed to 1 minus y cubed, x plus y cubed, e to the y times x plus y cubed, dx dy, by carrying out the following change of variables. U equals y, and v equals x plus y cubed. All right, good. Now, notice that they will always give us what change of variables we need to do. So we're not going to have to guess. They're going to tell us because they like us. They want us to succeed. All right, so essentially, remember, we have our 3 steps. 1, how do you break up? That's our Jacobian. 2, what's our function? We need to rewrite that in terms of our new variables. And 3, our bounds. And this is for every single integral problem. Every single integral problem you always encounter always has these 3 parts, and we need to make sure we understand. Once you understand those 3 parts, putting it all together, it's just a matter of patience more than anything. So let's start with the breakup. So we have our Jacobian. So let's see, we have u sub x, u sub y, v sub x, v sub y. You might object, Steve, I don't think that's what you wrote down. I can't remember what I wrote down. But again, it doesn't really matter. You just have to have one set of variables in one direction, say in the rows, other set of variables in the other direction in columns. And as long as you're consistent, life is fine. The Jacobian, it's a very forgiving matrix. So, u sub x, well, there is no x, 0. U sub y, 1. V sub x, well, 1. V sub y, 3y squared. So this determinant is 0, minus 1, negative 1. But remember, secretly, there's always an absolute value floating around. So our Jacobian is 1. Well, what does that tell us? Well, it tells us dx dy is equal to du dv, because the scaling factor is 1. All right, so that's not so bad. No real surprises to be seen here. Not yet. Okay, so now that takes us through the breakup. How about the function? So I don't need to pull anything aside. So I still have the whole function there, x plus y cubed e to the y times x plus y cubed. We say, well, x plus y cubed is v, so that'll take care of those pieces. And the last piece, that y, is u. So we can say this is v e to the uv. Okay, function, very straightforward. But you should always do the function after you do the breaking up, because there might be times when we grab a part of the function to be involved in the Jacobian. Okay, that brings us to our bounds. Okay, the bounds. We must not forget the bounds. Now, what do the bounds look like? Now, these aren't maybe the most convenient bounds that we've ever worked with, but that's okay. Why would that stop us? What do they look like? Well, we're told on the outer layer we have that we go from 0 up to 1 for y. So here, this is our y equals 0, and over here is our y equals 1. Now, for x, we go from minus y cubed less than or equal to x, and that's going to be less than or equal to 1 minus y cubed. Now, x equals negative y cubed. What that says is that I'm going to start here, and I'm going to start moving in that direction. I'm only going to go between 0 and 1, so by the time I've gone over here, I don't need to know this, but that's negative 1. It goes up beyond this. Now this 1 minus y cubed, it's actually the same picture, just translated over. So I just have to take the same curve and translate it over. So what we get is we get a nice little four-sided shape again. Well, that's kind of cute. All right, so there's our region here. Now that's our region as it's currently described. So in other words, this is in the xy plane. What we want to do is figure out the bounding curves. So if we think about the bounding curves, what do we have? Well, there's 4 of them. It's a four-sided object. 2 of the curves are really simple. We get y equals 0, y equals 1. Then we have the curve here. Minus y cubed equals x. Now I'm going to rewrite it by moving the minus y cubed across. So that's x plus y cubed equals 0. X equals 1 minus y cubed. Again, I can move the y cubed across. X plus y cubed equals 1. So these are the bounding curves in terms of x and y. We're going to rewrite every bounding curve in terms of u and v. So y equals 0. Well, that's easy to spot. That's u equals 0. Y equals 1. That's not hard to spot. U equals 1. X plus y cubed equals 0. Well, that's v equals 0. X plus y cubed equals 1. That's v equals 1. Which means, if we now move to the uv plane, we get a nice little 1 by 1 rectangle. So this is our new region. I'll call it S. S for new region. Well, that's probably not the most sensical reason to call it S, but I don't want to call it R because it's a different plane. See, I got to be careful. It's a different coordinate system is really what we're doing. That's really what we're doing. All right. Okay. Cool. So we now have our bounds. Now we're ready to go. So let's finish it. We've got integral 0 to 1, integral minus y cubed to 1 minus y cubed, x plus y cubed, e to the y times x plus y cubed, dx dy. And that's coming from, I'm just copying this down. Now, we just think of our process here. Well, dx dy is du dv. Based on our shape, it doesn't seem to matter whether we do du dv or dv du. So for right now, let's just start with du dv, and if we change our mind, we can change our mind. That's okay. X plus y cubed, e to the y times x plus y cubed, well, that becomes v e to the uv. And what are our bounds? Well, v goes 0 to 1, and u goes 0 to 1. Now, did we make a good choice? Well, when I say did we make a good choice, there's really only one place we could have chosen. Should we do du dv or dv du? Well, it looks like we got lucky. See, if we were going to try to integrate this with respect to v, oh, terrible things would happen. But, okay. But when we integrate it with respect to u, see, there's only a single u. So, that means we made a good choice this time. If it hadn't been that way, we would have changed it and switched the order of integration, and then we'd proceed. But now we're okay. All right, so let's see. What do we get? When we integrate this with respect to u, we still have our outer layer, 0 to 1, and then we have v, e to the uv, but remember we're integrating with respect to u, so we got to divide by that constant with respect to u, which is v. We're valuing that from u equals 0 to u equals 1 dv. Now at that stage, the v's are going to cancel out. Okay, so now we plug in our variables. So when we plug in 1, we're going to get e to the 1 times v, which is e to the v. Plug in 0, we get e to the 0 v, which is 1. So e to the v minus 1. All right, well, what is that integral? That's e to the v minus v. And we're going to evaluate that from 0 to 1. So, plug in 1, that's e minus 1. All right, are we done? Well, be careful. You always have to plug in 0. I know a lot of time, we say, it's just 0. But you always do it, just to be careful. See what happens, e to the 0. Wait, that's not 0. E to the 0 is 1. All right, so it's really e minus 1 minus another 1, which gives us e minus 2. And that's our answer. And now, yes, we are done. Good. All right, that's number 5. All right, well, let's try number 6. Oh, I remember this one. This is a fun one. I like this one because I was able to stump Wolfram Alpha. It's kind of a fun hobby. It's like, okay, let's see a problem that Wolfram Alpha can't do. And if we find it, we'll give it to the students to do. Just so that we can say, aha, look at us. We are better than Wolfram Alpha. Yes. So, number 1, breaking up. That's not so hard to do. 2, figure out what's happening with our function. 3, let's talk about our bounds. Again, 3 steps. So, the breaking up. Well, we have our substitution. So we're going to take our u sub x and our v sub x and our u sub y and our v sub y. And again, you can get away with a lot of forgetting right order of things. It's a very forgiving system. Okay, so what does that turn out to be? U sub x, well, 2x. V sub x, 1. U sub y, 1. V sub y, 0. So take that, it's negative 1. But of course, now we say, aha, we really meant to say an absolute value all the time, so we get 1. So what that tells us is that our dy dx is equal to du dv. In other words, the scaling factor, because this breakup, this is our Jacobian. So this right here, this is our Jacobian as a function of x and y. That actually, where that's showing up is it's times by 1. And really what's going on here is it says, it doesn't matter whether you go with the old system or the new system, it translates in a nice, convenient way. It doesn't always happen this way, but when it does, let's not fight it. Let's just embrace it. All right, so that's going to be easy enough for us to do. Okay, now let's go to the function. So our function, that's 6x cosine of x squared plus y cubed. Okay, because we're going to take the whole thing. None of this is being pulled up into the Jacobian. So let's think about what we have here. Well, we want to write everything in terms of u and v. Now the x, that's pretty straightforward. So that's going to be 6 times v. And we get cosine x squared plus y. Well, that's also pretty straightforward. That's u. All right, so there we go. There's our function. And pretty often our function is going to be a very straightforward change. And the reason that that's the case is because we're really making this substitution to make our function simpler. And so we should anticipate that things should get simpler. If they don't, we should be highly suspicious that we've made a mistake. All right, now comes the fun part. So our current bounds say our x goes between 0 and 2, and then y goes from this curve x minus x squared less than or equal to y less than or equal to 2 minus x squared. So let's see if we can get sort of a handle on some of these curves. I only need to go from 0 out to 2. I'll say this is 2 out here. 2 minus x squared. Well, that's a parabola. And if you think about that parabola, y equals 2 minus x squared, you take, start with just y equals x squared, the negative, flip it over, 2, shift it up. So you're coming up here to positive 2, and then it's going to open down, and to this point where down here at 2, 2 minus 2 squared is 2 minus 4. It's actually negative 2. So, okay, so that's the top one, x minus x squared. Well, it's not so hard to figure something out. So y equals x minus x squared. At 0, well, you'll be 0 minus 0 squared. That's 0. At 1, well, you'll be 1 minus 1 squared. So you'll be roughly here at 1. And then at 2, you'll be 2 minus 2 squared, which is going to be down here. So what it looks like is you're coming up, and then you're going down. So here are our two curves. Y equals 2 minus x squared. Down here, y equals x minus x squared. And what are we doing? Well, we are going in between those two curves. All right, now, here it's a little more interesting. How many bounding curves do we have? We have 3. 1, 2, 3. So, we're going to figure out what happens to each one of those curves. So let's be careful and write those curves down. The one on the left here, that's x equals 0. Well, that's not so hard to translate. Since v equals x, that becomes v equals 0. The next curve, y equals 2 minus x squared. Now, I can't help but I notice that there's this x squared plus y. So I can write this as x squared plus y equals 2, which says this becomes u equals 2. Now our last curve, y equals x minus x squared. Well, again, I see that x squared plus y, very tempting, and I'm going to yield to that temptation. X squared plus y equals x. Well, x squared plus y is u, and x is v. So I can rewrite that curve as u equals v. So my shape in the uv plane looks like what? Well, I have v equals 0. That would be this line right here. So this line, let me move it up a little bit so we can write down some notes. V equals 0. Then I have u equals 2, which is, I'll say here, u equals 2. And then I have u equals v, which is here, u equals v. So what we get is we get this shape. We get a triangle. So I have to pick the part that's bounded by those three curves, and there's my new region. So you'll notice that our old region is kind of hard to describe, but our new region, it's actually quite lovely. It's very simple and elegant. Okay, good. So we now have our new region. We are ready to go on to our next phase. Okay, integral 0 to 2, integral x minus x squared, 2 minus x squared, 6x cosine of x squared plus y cubed dy dx. The dy dx, all right, we know how to handle that. Before we do that, let me pause here. So that's 6v cosine u cubed. Now, dy dx, well, that's du dv. Okay, cool. So I'll just put that here, du dv. And what will the bounds be? Bounds. Well, where does v go from? I go from v equals 0 up to this intersection. Well, if we do the intersection, it's at 2. So v goes 0 to 2. And then if I were to slice that way, I go from u equals v to v equals 2. Now, cool. If we were only asked to rewrite, we'd be done. But we were asked to find. How do you integrate 6v cosine u cubed? That is correct. You do not integrate 6v cosine u cubed with respect to u. You can't do it. So what does that mean? Well, it doesn't mean we did it wrong. It means, hey, you know what? Let's change the order of integration. So, integral 6v cosine u cubed dv du. Now come to the picture. Where does u go from? Well, it goes from 0 to 2. Where does v go from? We go from v equals 0 to v equals u. Now, before we go any further, let's just point out how we should have known from the beginning to do that. Do you see this little thing down here? This is called 0. 0 is your friend. And anytime you can get 0 in the bounds, you're much better off. Notice here, we don't get a 0 in our lower bound. And so if you only knew nothing else but just the bounds, you would say, I would like to prefer the one with a 0. Because that's usually almost always going to be a simpler integral. All right, so now we're ready to keep going. So we can integrate 6v cosine u cubed with respect to v. And if we do that, what will happen is the cosine u cubed is a constant. So I'll just go ahead and write that in front, cosine u cubed. Integral of 6v will be 3v squared. And we evaluate v equals 0 to v equals u. So v equals 0 is nice, we're going to get 0. V equals u, we'll get integral 0 to 2 cosine u cubed 3u squared du. Ah, okay. All right. This looks like a substitution. And you're probably like, we should set u equal u cubed. But, well, we can't use u. It's already being used. So we've got to come up with new symbols. Well, instead of doing u, we can double down. We'll call this double u. Then 3u squared du would be dw. So if we update, well, u is 0, so w would be 0 cubed, which is 0. U equals 2, w would be 2 cubed, which is 8. Then we have cosine w dw. Well, the integral of cosine is sine. So sine of w, evaluate from 0 to 8. Sine of 8 is sine of 8. And sine of 0 is 0. So that goes away, leaving us with sine of 8, which is the right answer. Wow, what a fun problem. Cool. Wow, man. I miss doing problems like these. They're a lot of fun. They're a lot of fun. Now, for something completely different. After the last couple of problems, and sort of anticipating the last two problems on this quiz, these are going to fill out a place. But that's because we're sort of starting a slightly different topic. So we have a vector-valued function, y sine x, x squared plus 2z, xy plus e to the z. We're asked to find the divergence. Now the divergence of f, remember this is the one that comes from the dot product, del dot f, and where del is your partial derivative. Since we're three variables, so that's three-dimensional del, so partial partial x, partial partial y, partial partial z, dot f. So the way that the divergence of f works is you're going to take the partial derivative with respect to x of the first term, then you're going to add to that the partial derivative with respect to y of the second term, and then you're going to add to that the partial derivative with respect to z of the third term. Now when you're taking the divergence, you're not going to end up with a vector, because that's not what divergence is about. Divergence, you're going to end up with a function. So when we come to our first term, the y is a constant because we're taking derivative with respect to x. Derivative of sine of x is cosine x, so y cosine x. X squared plus 2z, there's no y at all. So that's, pooh, gone. The last term, xy plus e to the z, when I take derivative with respect to z, the xz term goes away. Derivative of e to the z is e to the z, and we're done. So in general, finding the divergence of something is actually a lot of fun. It's very quick, and as long as you remember that you're not supposed to end up with a vector, you're supposed to end up with a function, it's usually, I don't want to say it's foolproof, but it's almost foolproof, at least compared to other things. This is the kind of problem that students say, I hope this is on the quiz. Well, now we know. Not this time, but who knows? Who knows? Number 8. Okay. Suppose we have f equals y sine x, x squared plus 2z, xy plus e to the z. Well, that sounds really familiar. Well, yeah, we just did it. But now, see, there's been a change. It's not the divergence, it's the curl. What's the curl? Well, the curl, that's our cross product, del cross f. Or, again, partial partial x, partial partial y, partial partial z, cross our vector valued function f. All right, cool, good times. Here we go. How do we do it? Well, we're going to do our cross product. So we get the curl of f, and I like to actually do it as the cross product. It's going to be I, j, k. So when you're doing a cross product, first row is your vectors. Second row, partial partial x, partial partial y, partial partial z. That's your elements of your del. Also, this is sometimes called nabla, but I think usually people call it del. And then f. So that's your individual pieces. So y sine of x, then x squared plus 2z, and the last xy plus e to the z. This has got to be one of the most peculiar objects, because when you first see it, you're like, what? Really? Does this even make sense? Because you've got this determinant where the first row is vectors, second row is operators, and the third row is functions. And somehow, out of all of this, you get something beautiful. Now, we just have to be patient here. So, start working your way down the diagonals. In the I direction, take the derivative with respect to y of xy plus e to the z. Well, the derivative with respect to y of xy plus e to the z will be x, and that's in the I direction. In the j direction, take the derivative with respect to z of y sine x. Well, there's no z, so the derivative there is 0. So plus 0j. Now k, take the derivative with respect to x of x squared plus 2z. Well, the derivative of that will be 2x, and that's in the k direction. All right, so that's going down in that direction. Now we're going to go down in the other direction. So I wrapping around here, derivative with respect to z of x squared plus 2z. So take the derivative with respect to z of x squared plus 2z will leave us with a 2. That's in the I direction, but pay attention to direction that you go down, because sign matters when you're taking your determinants. J, derivative with respect to x, wrap around, of xy plus e to the z. So derivative with respect to x of xy plus e to the z will leave us with a y. All right, now that's in the j direction. And again, because of the way we're going, subtract. Last one, k, derivative with respect to y of y sine x. So that'll be derivative with respect to y of y sine x is sine of x. That's in the k direction, and again we subtract. Or we get x minus 2 in the first entry, that's the one corresponding to the I. 0 minus y, or negative y, in the second entry, which corresponds to the j. And in the last one, 2x minus sine x in the k. And that's the curl. So the input is a function, the output is a function. In some sense, this should be behaving like the derivative of that function, because that is what we're trying to do, is we're trying to get something that is derivative-like. And, well, I think we succeed to a degree. All right, well, that's not so bad. Definitely not as easy as divergence, but it's not so bad. You just have to be patient. And if you do a couple, they become pretty straightforward. Now, that brings us to our last two. All right, these ones, they're a little bit of a challenge, but that's all right. It's good to be challenged. It's good to, really stretch out and try to be a little bit more hard, do harder problems. So, we're going to evaluate this integral, 0 to 1, y to the square root of 2 minus y squared, square root of x squared plus y squared to square root of 4 minus x squared minus y squared, 2yz dz dx dy by converting to spherical or cylindrical. Okay, well, all right. Well, dealer's choice, right? And you'll get the same answer either way. I'm gonna go for cylindrical. I don't know why. You can, for fun, try it yourself later on. Do it in spherical. So both will work. Before we start, I think it's good to get an idea of what this shape looks like. So, let's start with y. We know y goes from 0 to 1. X, well, we're going to start at y, and we're going to go to square root of 2 minus y squared. Now, suppose I were to stop here. These curves, y equals x, that's not so hard. X equals square root of 2 minus y squared. That one maybe is not so obvious right away, but if you play around with it, you square both sides, you get x squared equals 2 minus y squared, or x squared plus y squared equals 2. So it's a circle of radius not 2, but root 2. So it'll come over here, here's a root 2. And it happens to intersect this line at 1, because 1 squared plus 1 squared equals 2. So our region in the xy plane is that shape right there. All right, so there's our nice, beautiful shape in the xy plane. Now, where does z go from? Z goes from root x squared plus y squared to z equals square root 4 minus x squared minus y squared. So, how do we understand that shape? Well, let's try this. First off, z equals square root of x squared plus y squared. That's not so bad. That's a cone, right? Yeah, it is a cone. So that's, z equals r. It's another way to say this. Now, z equals the square root of 4 minus x squared minus y squared. Probably an easier way to write that is x squared plus y squared plus z squared equals 4. Square both sides, move things around. So that says we're going to go up to the sphere. Okay, so this is a sphere of radius 2. All right. So, what's our shape? Okay, so this one is going to take a second for us to digest. So we're going to be slow here. And it's not because I think that you can't handle it. It's because I'm slow to think about these things. And it takes a while to sort of get a grasp. Now, if we think about what's going on here, this shape will translate down here. I have a root 2, becomes a root 2. I have this y equals x. That's this line y equals x. So I have this circle coming out. So what's happening is that this shape here translates into this shape here. And I think I got my circle a little bit shallow there, but okay. All right, so that's the lower shape. Now, what's happening above here? Well, above here, we're going from a cone. So we have this cone at z equals r. And we're going up. And eventually, we're going to have the top of it is going to be a sphere. So this is our sphere, x squared plus y squared plus z squared equals 4. So if we are very patient here, if we think about what's happening, when do these two surfaces intersect? So this cone, when does it hit that sphere? Well, notice here we'd get that the cone is, another way to think about that is z squared equals x squared plus y squared. So if we replace x squared plus y squared by z squared, we say, aha, they are going to intersect when z squared is equal to 4. Sorry, z squared equals 2. Because you get z squared plus z squared equals 4, z squared equals 2. Which says they intersect when z equals root 2. Which, all right, bear with me, says that if you look at this curve, that's r equals z, that says that this is directly below the intersection. So, what's our shape going to turn out to be? Our three-dimensional shape, it's kind of an interesting shape, but it's this sort of, the shape, I'm trying to think of the best analogy. I don't know if you've ever had like an ice cream cone. I have. I've eaten a lot of ice cream cones in my days. Not that many, but a non-trivial number. So you can think of the cone as like a waffle cone. Then you have ice cream that you sort of have a little nice layer on the top. And what you've done is you've taken a wedge out of that shape. So that right there, that's your shape that you're working with. I probably should make it a slightly different color than what's below. All right, so I'm going to just slightly different color than what's below. All right, so there we have it. There's our nice, beautiful shape. Good, good. Now, we start to dig into it. What do we need to do? Well, we need to think of our pieces here. So remember, everything has three pieces. There's the how you break things up. That's your dv. The function. And then your bounds. So we're going to go through and think about each one of these. So first off, what will dv become? We're going into cylindrical. So we're going to get integral, integral, integral. So dv will become r dz dr d theta. So this is our dv. Now the function, what will that become? Well, we want to write things in terms of cylindrical coordinates, so r, theta, and z. Z, good to go. How about y? Well, that would be replaced by something that works for cylindrical. So that's 2r sine theta z. So this is our function. Okay? Yes? Now the nice thing is the z part stays as z, so you just have to replace the y, and that's r sine theta. Now let's think about theta and r. You can actually get it because the theta and r are determined by the xy plane. So we think about it and say, well, where does theta go from? Theta, we start on the x-axis, and we're definitely hitting it, and we're going from 0 out up to this y equals x curve, which is at pi over 4. So 0 up to pi over 4. Where does r go from? Well, you think about coming from the origin out. So we come out until we hit that curve. Well, that curve is a circle. It's a circle with radius root 2. So we're going to go from 0 out to root 2. Where does our z go from? That's our last layer here. Now z, we actually know how it behaves. See, because we see it right here. Now z equals root x squared plus y squared. That's z equals r. That's where you start in the lower bound. So z equals r. How about the upper bound? Well, z equals square root 4 minus x squared minus y squared. Well, that's the square root of 4 minus r squared. Because we can replace x squared plus y squared by r squared. And now we're ready to go. We've got our setup done. We've got our bounds taken care of. It's a little bit crowded here, but we'll clean it up in a second. We've got our function, and we've got our dv. So let's clean everything up first. So we get integral 0 to pi over 4, integral 0 to root 2, integral r to square root 4 minus r squared. And then what do we have? Well, we have a 2z. We have r times r squared. We have sine theta. And okay, that's all our pieces, dz, dr, d theta. Now, we can't break into 3 parts, not yet, because we do have variables in our bounds. So let's integrate with respect to z. The r squared sine theta is a constant. Integral of 2z with respect to z will give us z squared. So 0 to pi over 4, 0 to root 2. So then we're going to have our, r squared sine theta, and then z squared, evaluate that from z equals r to z equals square root 4 minus r squared, dr d theta. Now, evaluate 0 to pi over 4, 0 to square root of 2. We're going to get r squared sine theta. We're going to square the square root. So that's going to leave us with just what's on the inside, 4 minus r squared. And we're going to subtract, when we plug in r, that's an r squared. Now at this point, now we can start to think about pulling it into 2 integrals. Because, notice, there's only constants in our bounds, and we can think of it as function of theta and then functions of r multiplied together. So, integral 0 to pi over 4, sine of theta, d theta. And we'll work on cleaning that integral up in a second, working out what that turns out to be. The other one, we're going to get 0 to root 2, and we'll clean this up. Now, let's be careful here. We have 4 minus r squared minus r squared. So that's 4 minus 2r squared. We're going to multiply that by r squared. So we get 4r squared minus 2r to the 4th dr. All right. Whew. Okay. Now, we got to work these 2 integrals. Let's work on this integral really quickly. Integral of sine is negative cosine. We're going to go from 0 up to pi over 4. And so that would be cosine of pi over 4 is minus root 2 over 2. Cosine of 0 is 1, so we have minus minus 1, which is plus 1. All right, so that's the first integral. Now, the second integral, what will that be? Okay, we'll do some work off to the side here. So we would get 4/3 r cubed minus 2/5 r to the 5th. And we're going to evaluate that from 0 to root 2. So that's the second integral. So the nice thing is when we plug in 0, we get 0. All right, finally, some good news. Plug in root 2. Now this is going to be fun. So let's be careful here. Root 2 cubed. If I think about what root 2 cubed is, I can say, well, look, that's like root 2 times root 2, which will give me a 2, times another root 2. Then I have 2/5 times root 2 to the 5th. So that's going to be 5 root 2's. So the first 2 root 2's will combine together to give me a 2. The second pair of root 2's, that's another 2. And then there's one last root 2 left over. So it's really a 2 times a 2 times a root 2. So the root 2 you can factor out. In fact, you can also see there's 4 times 2 and 8 here. So I'm going to say, look, this is really 8 root 2. And then we're going to multiply this by what? Well, from the first term, you're going to be left with 1/3. And then the second term, you're going to be left with 1/5. Now, a third minus a fifth, that's 5/15 minus 3/15, which will be 8 root 2 times 2/15, or that would be 16 root 2/15. Yes? I think so. Okay. Now, remember, that's going to multiply. That's the second part. So, combining these two together, we're going to end up with minus root 2 over 2 plus 1, which I'm going to write that as 1 minus root 2 over 2, times that by 16/15 root 2. Now the last thing I want to do here is I'm going to multiply this root 2 on the inside. If I do that, well, I have a 16/15 still there. All right, so that gives me 16/15. Root 2 times 1 is root 2. Now, root 2 times root 2 over 2. Root 2 times root 2 is 2. 2 over 2 is 1. So root 2 minus 1. And there you go. 16/15 times, whoops, I can't say that. 16/15 times the square root of 2 minus 1. Aha! We did it! It worked! And it got a little bit crowded, but I could argue I fit it on one page, so how bad could it be? Now, I will probably say that this is one that perhaps we're a little bit grateful is not on the quiz. Yeah, this one's a challenge, but it's good to be challenged. Okay, because that'll help us grow. We have one more challenge. Let's finish it up. Okay, number 10. Whew. Okay, looks pretty good. Actually, kind of looks really similar. So evaluate integral 0 to 1, integral x to root 2 minus x squared, integral root x squared plus y to square root of 4 minus x squared minus y squared, z squared dz dy dx. If this feels very similar to the last problem, it's because it's very similar to the last problem. Now, on the last problem, you said, look, dealer's choice. Cylindrical, spherical, whatever makes you happy. Here, we're definitely being told what to do. Spherical. So we're doing it. So let's begin again. All right, so be careful. What can we say about x? Well, x goes between 0 and 1. All right. How about y? Well, we go x is less than or equal to y, less than or equal to the square root of 2 minus x squared. If we combine these pieces of information together, well, we have the y equals x. We have y equals the square root of 2 minus x squared. Very similar to the last problem. That's x squared plus y squared. Whoops, that's supposed to be a circle here. So this is radius root 2. And what do we know? Well, root 2 here. We're going to intersect here at 1. So we're going from 0 to 1 for x, and then we're going from y equals x up to that curve. So in terms of the xy plane, that's our region. It looks like this nice little shape here. All right, good. Okay, that's a little bit different, but not so bad. Now, how about for z? What's happening for z? Well, it's actually the same bounds, right? So we get the square root of x squared plus y squared less than or equal to z, less than or equal to the square root for minus x squared minus y squared. So what's happening is I'm going to go up to, from the bottom cone, up to a sphere. So this here is a cone, up here is the sphere. Now, we don't want everything. We got to pay attention here. So it's not this whole shape, it's just a part of the shape. Now, which part do we want? So if we think about this as our xy plane, then we're going to go, according to the picture here, this piece. So this little piece here translates into the in terms of the xy plane into this little sliver here. And then we go up, and again, a lot of this is the same. So I'm not going to repeat all the arguments that we were before, but this bounding curve is exactly on top of that one. So what we've ended up with is we've ended up with a shape, again, it's the sort of wedge of an ice cream cone. It's just been sort of turned 45 degrees. But other than that, our shape, really, it's the same thing. All right, so there you go. There's our nice shape. Now we get to start the fun. And I think this is a case where it really does help to look in what I like to call the RZ plane. And this is helpful whenever you do anything that involves a rotation. And this is a shape that really fits itself well to rotation. The cone, that can be described by z equals r. The sphere, when I look in the cross section, this is a cross section, it's a circle that comes here at 2 and then comes down. And so here this is at root 2, and so what's happening is to form your shape, you're going to take this sliver here, and it's not a triangle, it's sort of it's a pi wedge, that's what it is. And you're going to spin it about 1/8 of a revolution. Okay, so there we go. We now have our shape laid out for us. So, as we did when we did the previous problem, we have to think about our pieces here. This dz, dy, dx, that's our dv. The z squared, that's our function. And then the rest of it is our bounds. So let's figure out what our new integral is going to become. All right, first thing is let's talk about z. So to do z, we want to think about what does z become in terms of spherical coordinates. Well, z becomes rho cosine phi. That's our basic formula for z. Okay, so this part right here, that's our function. How about dz, dy, dx? Well, that's our dv, and we just remember the song. Rho sine of phi, d rho, d phi, d theta. Done. How about theta? Well, theta, come to the xy plane. And you say, okay, where does our theta go from? Well, we start here at pi over 4. See, that's that nice 45-degree line. And then we're going to stop at pi over 2. So, theta goes pi over 4 up to pi over 2. Now, phi. Where does phi go? For phi, take a look at the picture. And what picture? In the RZ plane. So phi says, look at the positive z-axis. How far off do you come? So we actually start right away. So that says we're going to start at phi equals 0, and we're going to keep hitting our region until we are on this line, z equals r. What angle are we there? Well, that's the angle phi equals pi over 4. And then after pi over 4, see, you're going to be down here. You don't hit your region anymore. So, gone. Don't need to worry about it. Now, the last part, rho. Well, how does rho work? Well, come from your center out till you hit your shape. Well, what's this? That's our sphere. Now, it's a sphere of radius 2, which is rho equals 2. So we go from 0 out to 2. 0 to 2. Now, what do you see? I'll tell you what I see. I see some really nice bounds. Beautiful bounds. The reason I say these are beautiful bounds is that they only involve numbers. And we can break our function up. So what we can do is we can actually make our life quite nice. We say, okay, let's start with the theta. So the bounds are pi over 4 to pi over 2. And there's no theta function, so it's just d theta. Next level, phi. Bounds are 0 to pi over 4. Well, where's the phi? There's a cosine squared phi and a sine phi. So cosine squared phi, sine of phi, and d phi. How about the last layer? All right, so we're just going to break this up into 3 integrals. Last layer, 0 up to 2, rho squared, rho squared. So that's rho to the 4th, d rho. Now, some of these integrals are pretty straightforward, and the other ones are also pretty straightforward. We just got to be patient and make sure we don't rush ourselves and make mistakes, because that would be terrible. We've come this far. We don't want to make a mistake now. So here, the first integral, that's theta. Evaluate that from pi over 4 to pi over 2. Well, that's really pi over 2 minus pi over 4. And so if you evaluate that, that'll be pi over 4. That's pretty straightforward. That one's not too much of a surprise. Let's do the rho, because I think the rho one is also fairly straightforward, all things considered. Integral of rho to the 4th, 1/5 rho to the 5th. Evaluate that from 0 to 2. Well, if you plug in rho equals 0, you get 0. Plug in rho equals 2. That gives you 32 fifths. All right. Well, that's good. Now, one more to go, which is the middle one. Cosine squared phi, sine of phi. You're probably thinking, oh, this is going to be terrible, some sort of crazy power reduction. But it's not. It's not terrible, and it's not a power reduction. What is it? Well, what it is a substitution. See, if I have cosine, derivative of cosine looks like sine. Not quite, there's a small sign change, but we'll do a substitution. U equals cosine phi, du equals derivative of cosine is negative sine. So, what do we get? This will be integral. Cosine of 0 is 1. Cosine of pi over 4, root 2 over 2. Then cosine squared of phi is u squared, and sine phi d phi is a minus du. So there's a minus sign. Well, there's also the bounds are kind of in a weird order. So we'll just flip the bounds and get a better order. Root 2 over 2 to 1 of u squared du. So that would be 1/3 u cubed evaluated root 2 over 2 to 1. So that would be 1/3 times 1 minus, now cube this. Well, if I take the square root of 2 cubed, that's the square root of 8. And then 2 cubed is 8. All right, so what do we need to do? Well, at this point, what we need to do is we need to combine our three pieces. So there's 1, 2, 3 pieces. So we have pi over 4. Then we have 1/3 times 1 minus root 8 over 8. And then we have 32 over 5. Now, I can take this over 4, that goes into 32. So that would leave me with 8. And this 8, I can distribute through here. So what do I have? Well, I have a pi. Here I have a 1/3 and a 1/5, so that would make that 15. Then when I multiply the 8 through, that'll be an 8. And here the 8 cancels with the 8 in the denominator, which is why I did it, because I really wanted to cancel that, leaving us with 8 minus root 8 times pi over 15, which is the answer. Oh, what a nice answer. That was great. A lot of fun. These last two really got us to stretch ourselves and think geometrically. But you know what? A lot of multivariable calculus is about thinking geometrically. And so this is good to do these kinds of problems. Well, that's our last one for this quiz. But don't worry, one more quiz. It's going to have a lot of fun problems. Something to look forward to for next week. But we're done for this week. So take care, my dear friends. Thank you for watching, and we'll see you then. Bye.